Good afternoon, ladies and gentlemen. It is time for this session. First, let me introduce myself. My name is Yan Chun Wen from China Society for Change Technology in Beijing. This is my first trip in Jeddah and first time attending a Lab World Week. So it's my great pleasure for as the chairperson for this session on paper rehabilitation. In this session, we have three presentations with 20 to 25 minutes each. So at the end of this each presentation, we have 5 to 10 minutes for questions. And at the end of this session, if we have time, we can have open discussion on any papers presented. The first presentation will be made Dr. Mulat, and his presentation title is The State of Condition Assessment and Rehabilitation of Large Diameter Concrete Pressure Pipes in the U.S. Dr. Mulat is a member of SGH Engineer Mechanics and Infrastructure Group, specialized in condition assessment and rehabilitation of pipelines and fiber reinforced polymer composite application. He has experience in analysis, design, and test of FRP for the use in rehabilitation of infrastructure as well as in new construction. His experience spans hundreds of projects for water and power utilities, including some projects at nuclear power plants, extensive experiments, and analytical research, as well as more than 25 publications. Dr. Mulat participates in professional committees at AWWA, ASTM, ACI, and ASCE. So, please, Dr.
Thank you very much. Sorry, there was something else on my screen that was different from the presentation. So hopefully this should work. Okay. So thank you, Mr. Chairman, and distinguished guests. Thank you for being here right after lunch, first of all. It's my pleasure to be here visiting from the United States to share some of our experiences, specifically in condition assessment and rehabilitation of large diameter pipelines. So what we are talking about is primarily, but not necessarily limited to, large diameter pipes between, let's say, the source of the water to a water treatment plant. The source can be a lake, a river, a dam, bringing the water from long distances potentially in high pressure, or as well as bringing that water from the water treatment plant to the distribution system. So these pipes are used widely in the United States historically, as well as around the world. And we understand that in the Middle East as well, because historically there have been, for example, pre-stress concrete pipe manufacturers in the Middle East that serve this area over many years. So there are a number of pipelines, a vast amount of pipe of this kind in the ground in this area as well, to our knowledge. So, like I said, I would like to share some of our experiences in this area and what we do in the United States as a summary, and with some couple of case studies. Before I get into the presentation, just a brief word about the company that I come from. Simpson Gumperz & Hager is an engineering consulting firm. We are not necessarily affiliated with the inspection technologies that I will talk about, or rehabilitation contractors that install some of the techniques that I will talk about. But what we do is serve as the bridge, if you will, between the owners and other stakeholders like contractors or inspection companies and so forth. We assist the owners in coming up with their condition assessment programs, developing asset management plans, investigating the failure risk of their pipelines, and making recommendations as to what methods should work best for their systems. We are based in the United States and a 60-plus-year-old company, but we also serve other areas of the world. We operate in more than 30 countries. And some of our contributions to the industry are not only doing projects for owners, but also try to improve the know-how in the industry by doing research and developing standards. Some of the standards that we significantly contributed to are shown on this slide, ranging from the design of pre-stressed concrete pipe, which is AWWA standard, C304, the manual that goes into more details of that design approach, condition assessment best practices manual, and most recently, we assisted and led the development of the CFRP, carbon fiber reinforced polymer renewal of concrete pressure pipe, which just came out a couple of weeks ago, actually, as a new standard, AWWA C305. So first of all, what is the problem that we are dealing with? As you might know, in the United States, American Society of Civil Engineers grades the infrastructure almost like a school grading system, ranging from A to F. And every 4 years, they assign an infrastructure grade, the last one being in 2017, which was a D+. The meaning of D is a poor and at-risk condition. And if you look into water infrastructure specifically, that grade, in fact, is a D, not even D+. Some of the specifics that come out of that poor condition is that American Water Works Association estimates that we need about $1 trillion over the next 25 years to maintain and expand water service. And other statistics is that we have about 2 million kilometers of water mains in the U.S., and we suffer about 240,000 water main breaks per year in the whole country. And this is partly because of the infrastructure age, obviously. A lot of our pipelines are very old, ranging from 50, 60, 70, 80-year-old pipelines in the ground. So as you can tell, the replacement of the pipe, just because it's old, cannot be the solution to this problem. As a result of that, in the last decade, couple decades in fact, the efforts and investments have focused on identifying those pipes that are individually distressed, that can be rehabilitated and their risk evaluated first, obviously, to maintain the reliability of the pipeline, as opposed to let's replace this whole pipeline just because it's 60 years old. And if you look at the largest utilities in the United States, about 90% of them use concrete pressure pipe in their system. So just as a quick refresher, what are we talking about in concrete pressure pipe? There are multiple types of it, about 4 different types listed under AWWA. Here is one example of it, most commonly used, a pre-stressed concrete cylinder pipe, which basically is a steel cylinder that provides water tightness to the pipe, that is embedded in a concrete core that provides the pipe to be able to resist the gravity loads, the earth loads and so forth, traffic load above. And on top of that, there are the pre-stressing wires, or sometimes non-pre-stress reinforcement, that are wound on the pipe to give it the pressure capacity. And the final component of it is the mortar coating, whose job is to protect that reinforcement from corrosion and the environmental factors. So just to back up here, you can see the history of the use of these pipes. The smaller diameters called line cylinder pipe and bar wrap pipe have been in use since early 1940s, and the larger diameter ones, as the need for such pipe developed, have been in use since 1950s. And there's a ton of such pipes in the ground in the United States, therefore reaching their useful life and in need of evaluation and rehabilitation. So how does the failure process of concrete pressure pipe actually occur? As I mentioned, most of the degradation comes from outside, depending on the use of the pipe. But if we're talking about water pipe, it is primarily occurring from the outside, which starts with some kind of degradation in the mortar coating, either due to the quality of the mortar or from environmental factors, perhaps the pipe being in a severely corrosive environment or something like that. Once the mortar coating is cracked, now the pre-stressing wires behind the mortar coating are subject to the environmental factors. They start corroding and start breaking. And as the pre-stressing wires break, the original pre-stress in the pipe is lost. The pipe decompresses, and eventually the concrete core cracks. And after a certain length of degradation in the pipe, this is what happens: the pipe bursts. And this is not an uncommon situation. It happens. Once in a while, we see these on TV. I'm sure you have seen as well. The good news is that in a given concrete pressure pipeline, the number of pipes that in fact are degraded and therefore potentially in need of rehabilitation are limited to 4%. That covers statistics from previous inspections of pipelines. And another good news is that among those 4%, if you analyze them in detail, the ones that are actually in imminent danger of rupture are about 1%. So if you have pipeline that consists of thousands of pieces of pipe, in fact, by finding those that are distressed and rehabilitating them, could be a handful of pipe pieces in the pipeline system. So it is something to keep in mind, therefore not necessarily considering replacement as a first option. When it comes to condition assessment, there are three main questions that come up. One of them is where to start if you haven't started a condition assessment program before. The second one is which method to use. And the third one is, once we do the condition assessment inspections, what do the results mean? The question of where to start is the main question that challenges major utilities that have large systems of pipeline networks and at the beginning of their condition assessment program. So they are willing to invest some money into condition assessment. However, which pipeline should they inspect first? This is addressed by what we call the failure risk ranking, looking at multiple parameters involved in the question and basically defining the risk of pipeline as a multiplication of the likelihood of failure times the consequence of failure. So the higher the likelihood of failure and the higher consequence of failure is, you identify those pipes that are at higher risk, and those are the ones you actually invest in terms of doing a study on them. And these boxes basically define the parameters that go into the determination of the likelihood of failure, ranging from pipeline age, manufacture, quality of material used, and the performance history of the pipeline. And here we have the factors that go into the consequence of failure. What happens if a particular pipe fails in this pipe versus in that pipe? Is there a danger to life, property damage, service disruption in the downstream areas, and so forth? So after such a study, the areas of the pipeline network are assigned certain risk factors, and the highest risk ones, shown as an example here in the red ones, are tackled first. And then the next question is the method and the technology selection to do the condition assessment, which basically depends on two sets of parameters. The first one including the risk that you just identified previously, the level of information that is needed. Are you looking to get a general sense of the pipeline condition, or do you actually want to know every single wire break, pre-stressing wire break along the pipeline? what operational constraints do you have? Can you shut down the system? Can you dewater the system? Or do you have to inspect the pipeline in service and so forth? On the other hand, before selecting a method, you need to understand the available technologies, their advantages, disadvantages, and what uncertainties would they have if you use it on that particular pipeline at hand. In the following 4 slides, I would like to show you the 3 main methods, although there are small variations of them used. I'll show you 3 examples that we widely use in the United States. The first one being the simple visual and sounding inspection of a pre-stressed concrete pipe or other concrete pressure pipe, which is allowing you to identify pipes that are in their advanced stage of distress, especially in cases where the that particular pipe class is not very sensitive to distress. There are certain classes that can rupture abruptly, even with short lengths of pre-stress loss. But if it is not that sensitive, this method works really well and at a very low cost. It is very widely used in the industry. Most utilities have some program to shut down their system in a periodic basis to allow such inspections to occur proactively. So what you are looking for is, by using trained inspectors, not just some average technician that looks at any crack, but some trained technician who knows the degradation process of that particular pipe, sounds and evaluates the observations to identify hollow sounding areas, longitudinal cracks, and what do they mean in that particular situation. The second inspection method is what we call the acoustic inspection method. This is one step up, basically, from the visual and sounding. It is referred to as a survey level inspection technique in general. The advantage is that it is a non-invasive technique. What it does is basically sensors being installed on existing pipeline features like hydrants or valves or something like that. Or if they don't exist, they prepare a pothole to allow access to the surface of the pipe to lower a sensor there. But the pipeline remains in service while you do that. And then a noise source is created outside the bracket of the sensors, and they measure the speed by which that acoustic wave travels from one sensor to the other. And using that information, we are able to calculate the average stiffness of the pipe, and then calculate that stiffness to the stiffness of a good pipe. Based on that ratio, we can opine on whether within that segment there is a likelihood of distress pipe segment being